Hello. Today we will be observing the motion of a falling stress ball to test the efficiency of Newton's second law of motion. We will compare our observational data to a computational model with and without drag force. First, let's look at Newton's second law and the forces acting on our object. Newton's second law states that the final velocity equals the initial velocity plus the net force times the change in time divided by the object's mass. In our experiment, velocity is not constant. It is affected by the weight force due to gravity and the drag force caused by air resistance. The weight force is equal to negative mg(j), which means the object's mass times Earth's gravity multiplied by a unit vector to show the direction. The drag force is equal to the proportionality constant times the magnitude of the velocity squared, since we are calculating turbulent drag, and then multiplied by v hat, or the unit vector for velocity, which shows its direction. To the right is the Python representation for each of these equations, which helps us create our computational model. Now let's look at our experiment. I use the height of the fire alarm to calibrate distances in tracker, and I align the axes so that our object drops along the negative y-axis. Now let's play the video. I use markers in order to watch the object's motion and analyze it. As you can see in our position versus time graph, the velocity is increasing over time, as velocity is the slope of the line. Now let's view the code without drag on the left and with drag on the right. We input the ball's mass and the initial position based on tracker, and since we're dropping the ball from a resting position, we know that the initial velocity is going to be the vector 0, 0, 0. Now in our loop, we have the equations that we used to calculate our net force and the new velocity and the position for each time step. Our loop is going to run until the model's time equals the experiment's time, as seen here. By using arrow scale, we can create arrows representing gravity and drag force. The difference between these two models is that in one of them, the one on the left, there is no drag force, and Fnet is simply equal to the weight force. When we run the model with drag force, we can see that we obtain a graph very similar to the graph that we have in tracker. Also, this blue arrow represents the drag force, and the yellow arrow represents gravity. As time goes on, the drag force increases, while the force of gravity remains constant. As you can see, here I've used Excel to plot our observational data, represented by the green dots, with the computational model and with and without drag. In the without drag model, in the blue, the position of the ball is overpredicted since it does not account for the drag force slowing down the ball. In the model with drag, it follows our observational data far closer, as it accounts for the air resistance that is working against the weight force. So now the question comes up, if the drag force becomes large enough, does the object reach a terminal velocity? Theoretically, yes, it does. But in our experiment, since it fell such a short distance for such a small amount of time, we do not observe the terminal velocity being reached. This means that we don't see the weight force equaling the drag force, which causes a constant velocity or zero net force. What if we were to throw the ball down instead? In this case, the terminal velocity would be the same as an object drop from rest. This is because an object in a constant environment will have the same terminal velocity despite its initial velocity. Using a computational model, we can test this by setting our initial velocity to something other than 0, in this case, negative 3 meters per second. As you can see in our velocity versus time graphs, both objects reach the same terminal velocity, even though one starts with a faster initial velocity.